now?
Yes.
Okay. Good morning. Today I will start the Ionospheric section. I invited the speaker Dr. Lucila Fonsi, which the work is entitled The Study of the Ionospheric Irregularities on a Global Scale. Please, Lucila, could you please to share your presentation?
Yes, I try to share.
Yes. You have 40 minutes included the questions, okay?
Okay, can you give me
yes,
some kind of alert 5 minutes in advance?
Okay.
Thank you so much.
Thank you.
Okay, so thank you a lot for inviting me. Thank you in particular to Marcio Muella for this possibility. I'm here to give you an overview of our effort in studying the ionospheric irregularities at global scale. The concept is that generally the ionospheric irregularities is a term that refers to an irregular distribution of the free electrons in the upper atmosphere. This irregularity is meant as in time and space. So typical examples of irregularities are plasma bubbles, auroral blobs, polar cap patches, but also traveling ionospheric disturbance. And why we care about the irregularities? We would like to study the irregularities because we want to learn more, of course, of the ionospheric plasma, but in particular to support the space weather application. In which way we can study the irregularities? There are several ways, actually. The most used are the use of models and actual monitoring of a combination of these two approaches. And the open questions that we have to keep in mind are the discovery, the searching of the process ruling the formation and evolution of the irregularities, how we can predict the occurrence of the irregularities, how to predict the space weather impact of such irregularities, how to mitigate that impact. These are the open questions. So what we have done in the past years, and we are still ongoing on this pattern, is to use a combined approach of climatology versus weather, in the sense that we use the climatological assessment to understand on long-term scales. So long-term we mean years or also tens of years with respect to the weather, so the short-term variation in the upper atmosphere. This combination, the combined use of ionospheric weather, ionospheric climate, can help a lot in revealing the irregularities. But we have to keep in mind that we have also a climatology, so a long-term investigation of the irregularities, because we can recognize some recurrent features in the weather of the irregularities that we can describe as the irregularities climatology. So the concept is not so straightforward, and there is this dualism, this twofold approach of the climatology versus weather. This is an example of climatology of the irregularities. We have the fortune to own the longest data set of GNSS scintillation data ever collected in polar regions. In particular, they are collected in the high Arctic region, in the Svalbard archipelago at NEOLIS, a village that is completely dedicated to science. And this village is an international location for researchers that would like to exploit the natural lab provided by the pole. In that location, we have installed our first receiver in 2003 for detecting the ionospheric scintillation. So at certain point, close to the end of the solar cycle 24, we decide to analyze the entire data set and to try to extract a detailed assessment of the long-term behavior of the ionosphere under solar maximum and solar minimum conditions. We have also exploited a more recent possibility to explore the data collected by multi-constellation GNSS receiver that was installed in NEOLIS in the same location at the end of 2015. And we have stressed our assessment by trying to understand what is the actual weight of the choice of the cutoff frequency for the phase trending at climatological level. Sorry. So what we have done is to drive a realistic assessment of the high latitude scintillation to contribute to the improvements of forecasting model, because with a so long data set, we could provide a climatology of those irregularities that can impact the technological systems. So this is the location. In this GIF, in this animated GIF, you can see with this dashed circle the field of view of the station that is here in the black dot, and the position, the average, so the climatological position of the auroral oval boundaries under quiet on the left and disturbed condition. And you can easily see that NEOLIS is mainly a cusp station that under certain conditions can be also within the polar cap. So from September 2003, we had data from a Novatel GPS receiver, and in November 2015, we have installed a September receiver capable also to track the Galileo and GLONASS constellation. This is the NEOLIS location, our antenna, and what you are seeing is nice Norwegian style house is the Italian base station that is called Dirigibile Italia in NEOLIS. So this is the plot collecting all the conditions that we can see reflected in our monitoring. So as you can see, we have a significant number of strong, severe, and extreme geomagnetic condition, but also with moderate condition and with a lot of data collected during quiet conditions. So what we monitor in particular are the scintillation indices that are defined as here reported, just to remind you what we consider the scintillation indices. And for what concerns the entire data set that you can see as two big gap of data here between 2009 and 2010 and here in 2013, but anyhow with a good coverage along the period from the end of 2003 and the end of 2017. You can see that if we look at the phase scintillation given by the sigma phi index that is in blue is significantly higher along the entire period than the same occurrence of S4, so of the amplitude, as you can see in green, in light green. And the red curve represents the behavior of the R12, so is the solar sunspot number. And as you can see, this high occurrence with respect of the phase, what we call phase scintillation, with respect to the amplitude scintillation. A little bit of summary about the meaning of amplitude and phase scintillation and what we can derive from a spectral analysis of the raw signal received at ground. Essentially, the density function as function of the frequency can be described, ideally, of course, described by this kind of plot in which you can see that there is a changement of the slope at a certain frequency that is called the Fresnel frequency, that is related to the first Fresnel zone. And you can see that the other line is straight, does not show two slopes as in this case. This is representative of the amplitude of the signal. This is representative of the phase of the signal in case of scintillation. So there is these two completely different behavior of the spectral density function. Ideally, the best cutoff that has to be used for the trending the signal is the one that is equal to the Fresnel frequency, so to the changement of the slope. And why we have to trend the signal for phase scintillation assessment? Simply because the signal is non-stationary, because it's affected by the Doppler shift due to the satellite receiver motion that induce a trend, and by the slowly very background ionosphere and by scintillation. So we have to detrend the signal to extract the necessary information. The firmware of this scintillation monitor is set by default to have a cutoff frequency used for the trending at 0.1 Hertz. That means by simple computation that we are assuming that the velocity of the ionosphere is around 40 meters per second. But very, very often at high latitude, this is not the case. This is an underestimation, an heavy underestimation of the actual velocity of the ionosphere at high latitude. So the idea is to try to find the best cutoff frequency to be realistic and to remove the trend induced by the velocity of the satellite. This is an attempt that you can see with different cutoff frequency. At 0.1 Hertz, you can see by default by the receiver, this is the picture in geomagnetic latitude coordinates with the moon at the top here of the occurrence of phase scintillation greater than 25 radians. And you can see this is the picture along the entire data set from 2003 to 2017. But as you can see, if I change the cutoff frequency with a different choice, the picture is completely different. And also here and here, you can see the picture is completely different. And if we compare the picture of the phase scintillation with the picture of the amplitude scintillation that, as we have seen, doesn't have the problem of choosing the best cutoff frequency because it doesn't need to be trended, we can see how different is this picture of the amplitude scintillation with respect to this one. That is the default choice of 0.1 Hertz of cutoff frequency. In principle, we shouldn't have this great difference between the amplitude and the phase scintillation. I will say why in a few slides. So looking at this representation of the scintillation, I would say that the best choice here is more related to a frequency, a cutoff frequency of 0.4 Hertz or 0.25 Hertz, with a higher velocity of the ionosphere, and the ionosphere that actually is more realistic if we look for instance, to super down radar measurement or other kind of instruments at high latitudes. The problem is that at climatological level, it's very, very hard to assign the optimal cutoff frequency, simply because the conditions at high latitude are so dynamic, are so fast moving, that of the velocity of the plasma, that it is almost impossible to decide a fixed cutoff frequency level to be referred with when we deal with high latitude ionosphere over 15 years of data, over years of data. So it's a very, very difficult task. And you can see here how different is the picture of the phase scintillation and amplitude scintillation for different level of geomagnetic storm that are reported here on the top. And again, we should try to call scintillation only those regions of occurrence when we see also amplitude scintillation. For instance, here and here, close in the pre-midnight magnetic sector, we could rely on this representation. But for the cusp region, we should try to reason, to look at this enhancement more as a phase fluctuation instead of a phase scintillation. And we have tried to do this exercise in this recent paper published on Scientific Reports. So, passing from a climatological study to a case study of our research of the best cutoff frequency to be applied for phase detrending, we have applied another approach to our Antarctic data, because we collected also data in Antarctica. The approach starts from this assumption. What we call phase fluctuation, so when we see fluctuation on the phase of the receiver signal, two mechanisms are concurring. One is due to the diffraction, and is due to the presence of small-scale irregularities, and the other is due to the refraction, that is due to all-scale range and scaling with a factor 1/f. The diffraction is a stochastic effect. The refraction is almost all related to the deterministic effect. Not all, but almost the bulk of the effect is deterministic. If the cutoff frequency that we are choosing for the trending the phase is wrong, so to speak, the phase scintillation value includes mainly phase fluctuation that is not related to scintillation, but is related to refraction, so to deterministic effect, because we are overestimating the sigma phi. So the idea is to find a way to identify the cutoff frequency that is close to the Fresnel frequency, when there is the change of the slope in the amplitude of the signal from the spectral analysis. We have done this by using the ionospheric free linear combination to take into account the bulk of the refractive effects. And we are supposing that the crossing point between the carrier frequency, the two carrier frequency phase power spectral density, and the ionospheric free linear combination power spectral density can identify the new cutoff frequency. So to do that, we have used a new approach that is called fast iterative filtering. Is a nonlinear analysis method that from a mathematical point of view is more robust with respect to other methods as for instance, the Fourier analysis or the wavelet analysis, and applies this to one chop of data. You can see here we are seeing 30 minutes of data from the GPS satellite G26 from Concordia Station in Antarctica, and apply this approach. We have found the best cutoff frequency here in the crossing point among the ionospheric free linear combination and the phase and the amplitude on the signal on L1 and on L2. Here you can see the result. This is the sigma phi versus time. If you use the cutoff frequency at 0.1 Hertz, as given by default by the scintillation monitor receiver, you obtain the black curve. This is reconstructed by the VIII analysis, and this is what is given by the post-process data provided by the receiver, the blue curve, so they are in good agreement. But if you apply a cutoff frequency with the frequency that you derive from this exercise, the level of the phase scintillation is much lower than what is given by the computation on the base of the cutoff by default provided by the receiver. If you compare the S4 that is in blue with the sigma phi calculated with the new cutoff frequency, you can see that the behavior is very, very similar in the changes. And this discrepancy is likely due to the fact that not all the refraction is due to deterministic effect, but there is also a portion that is stochastic that cannot be eliminated by using this exercise. But anyhow, we consider this assessment of the scintillation of the phase scintillation level more reliable than this, the one derived from this approach. If you see from these case studies that we have analyzed, the correlation between sigma phi and S4 is improved if we use the adaptive choice of sigma, of the cutoff frequency, sorry. That are the one that you can see in this table. So starting from this, moving from this and going towards an empirical assessment of the ionospheric regularities and moving from high latitude to low latitudes, we can see a couple of examples of the multi-instrument approach, so completely or almost completely empirical approach to assess the irregularities at low latitude. This is an example from a very recent paper on JGR, which we have used a number of these different sensors to study this geomagnetic storm happened on August 2018 in Brazil. So you see we have used the GNSS receiver, the ionosones that are not shown in these slides. Some information derived from in situ data collected by the China Seismoelectromagnetic Satellites XS01 and Swarm ANC satellites that have almost the same local time and fly inside the ionosphere because they are LEO satellites. And we have used ground-based magnetometers for the assessing of the equatorial electron jet. This is the ground-based network, as you can see, quite well covered by GNSS, not so covered by Ionosonde, and we have also a couple of magnetometers that we have chosen in those locations for assessing the equatorial electrojet. This is a picture that summarizes the condition of the geomagnetic storm that we have studied. In yellow, you see the time of the swarm A, and XS daily tracks for your reference. This was a quite severe geomagnetic storm, and also with some injection from the high latitude of Joule heating that induce also perturbation at a lower latitude. So we can see here some examples of the different phase of the storm, in which in this case you see a representation of the electron density measured by swarm A satellite together with the vertical TC computed mapped along the track of the satellite at a fixed and thin shell 350 kilometers from the ground base station. The same exercise with the XS satellite in red. And in this plot, you see the behavior of the geomagnetic field as seen by the magnetometer, and at ground as seen by the swarm satellite with this black dot. In this case, in this phase of the storm, we were under counter electrojet condition driven essentially by the Sternbach dynamo conditions. And there is a broad electron density peak that is not catch by the TC estimated by ground station because of the poor coverage, but is seen from the behavior of the in situ data. Moving at the following epoch, we see the concurrent combination of prompt penetrating electric field and the Sternbach dynamo that gave rise to control electrojet condition that cause also the enhancement of ionization at middle latitude, as you can see here, that is very well visible in the swarm A assessment of the ionospheric condition, less visible in the XS representation, but you can see here how different were the path of the two tracks in view. So you can appreciate also the difference in the assessment of the two maps. The following step is to show you another kind of condition that we have encountered studying this storm. In this case, we have an equatorial electrojet condition that we think are caused by the forcing from below due to the planetary wave or Rossby waves, because analyzing long-term data, we have found a period of 3.8 days in the wave that we have found in our assessment. So we are quite convinced that the forcing in this case was not related to an external forcing due to the solar perturbation and the geomagnetic perturbation, but forcing from the lower part of the atmosphere due to the planetary waves. So that's all for the first case. And now I move to India for another case study. The storm occurred in September 2017. In this case, we have used a ground-based network that you see in the map. The GPS station are in green, magnetometer are these two in red. We have used a subset of the GPS station for TIDs detection and for the roti time profiles, and there are also a couple of scintillation monitors in this sector. This is again a representation of the general condition recorded during this storm. Again, also in this case, the study was recently published. And as you can see, also in this case, we have injection from the jowleting from the two caps. In this case, this was the behavior of the geomagnetic storm with the strange two-phase storms, in the sense that after a first recovery phase, we see another minimum, and then a slow but long recovery phase after the second minimum of the CMH.
Dr. Lucila, you have 5 minutes. You have 5 minutes, please.
Okay, thank you so much. From this study, we have seen that on 8th of September, there is the bulk of the irregularities formation. In this case, in green, we see the rate of TC index greater than 0.5 TC units per minute, and the black dots are related to S4 greater than 0.3. The sides of the dot and of the diamonds related to the intensity of these two quantities. These are the terminator of the sunset at E layer and at F layer. This is the deep equator, and this is the geomagnetic equator. This is the average position where we expect to have the crest. As you see, in this part, we see the bulk of the roti enhancement, and also the appearance of scintillation in the post-sunset region. And we see the climatological assessment of along the entire storm. We can appreciate how the 8th of September show a shrinking towards the equator of the northern crest of the equatorial anomaly, likely due to the depleted E cross B that limits the uplift of the ionospheric F layer in the noon and afternoon sector. From this movie, you can appreciate from the gradients of TC in particular, the presence of big depletion of TC and the appearance as black dots of the scintillations. And with this exercise, we are capable in our study to determine that these bubbles are migrating from other zone with a northward propagation, while this one is more related to the freshly generated sources. This is another part of the same study in which we have used a couple of stations of GNSS station meridionally distributed to assess the identification of large-scale TID that move with an estimated period of about 25 minutes northward. So, final remarks of my presentation. We are convinced that the advancement of knowledge in understanding the ionospheric regularity is fundamental both for scientific and space weather purposes. To do that, we can rely on model and data, and it generally is very effective to combine a climatological and weather description. keeping in mind that also the regularities show a climatological behavior. And the ideal case is to rely on an empirical representation based on measurements. And the integrated use of in situ and ground-based data revealed to be very effective to provide insight on irregularities origin, formation, and evolution. And we are collaborating all over the world, also with Marzio. That is why I'm here, and I thank you a lot again, to advance the current knowledge, because we are convinced that only a huge collaboration among all the community to share data and knowledge is the way to proceed. Thank you a lot for your attention.
Thank you, Dr. Lucila, for your nice presentation. You have some question in the chat, but
okay.
You have a time for 2 or 3 questions. I call Marco Silveira, the first people that question here. Marcos, please.
Hello, thank you for such nice presentation. I have more for curiosity. I'm not an expert on the ionosphere subject, but for how long would these irregularities stay in the ionosphere after the geomagnetic storm?
It's a very good question, but it's very difficult to answer, in the sense that not all the irregularities remain the same location for the same time, in the sense that it depends very often by the geomagnetic condition itself. You can have a sort of stagnation of the ionospheric plasma, in which the same irregularity can be visible for several minutes, also hours. Or you can have a fast-moving irregularity, so you can see only for a few minutes, and that's all in the area of interest. And it's very related also to the location that you are investigating. For example, at high latitude, you have in general a faster evolution, while at low latitude the evolution is lower. But again, it depends on the condition case by case.
I see, thank you.
And the other question here, it's only 9 gifted. The question is, are there any difference between plasma blobs and the auroral blobs?
Plasma bubbles, but
the blobs is different to the bubbles, I think. I don't know if
yes. The difference stands in the mechanism, essentially, and in the fact that the bubble are related to depletion of electron density, while the blobs are more related to enhancement of electron density. But anyhow, the mechanism of formation are completely different, because plasma bubbles are typical of low latitudes, while auroral blobs, as the name, are typical of the auroral regions.
Okay, thank you. And another student asked you, how long do the counter-electrojet conditions last for, and what are the causes?
Okay, again, this is the answer is very similar to the first question, in the sense that the counter-electrojet condition has to be studied case by case, and the two main sources for counter-electrojet are the prompt penetrating electric field and the disturbance dynamo. Both these mechanisms, these physical processes, are due to the geomagnetic storm evolution, and are related to the prompt, so very sudden reaction to the geomagnetic storm that induce the penetration of electric field from high latitude to low latitudes, and a delayed effect due to the disturbance dynamo that is due to essentially to the yaw heating at high latitude that induce a changement in the neutral dynamics of the thermosphere that induce again disturbance on the regular, so to speak, dynamo. So these are typical of the geomagnetic storm conditions.
Thank you. Do you have other questions in the chat, but you have done time for this. But if it's possible to answer in the chat, the people are interested in your work. So thank you so much.
Sorry, Liza, am I right that after the next presentation, there will be another presentation by me?
It's true, it's true. Okay.
Thank you, just for
so
confirming.
Much.
Okay, thank you so much. I quit sharing.